The night sky does not rush to explain itself, it simply waits. There are moments, quiet, almost invisible, when the world softens just enough for you to look up. The noise fades, the urgency of the day loosens its grip, and above you, stretching farther than thought can follow, is a darkness scattered with light. Not empty, not silent, just distant. People often say they look at the stars searching for answers, but that isn't quite true. Not at first. We look because something inside us responds before we understand why. A quiet pull, a feeling that what we're seeing matters, even if we cannot yet explain it. Somewhere in that stillness, a question begins to form, not loudly, not urgently, but persistently. How many of those distant worlds could hold life? Not life like ours necessarily, not cities or voices or familiar shapes, just something aware, something alive. And if that question has ever crossed your mind, even for a second, then you're already part of this journey. Before we go any further, if you find yourself drawn to questions like this, quiet, expansive, and just a little unsettling, consider subscribing and following the channel. Because this isn't just about finding answers, it's about learning how to sit with the questions that change the way we see everything. Now, let's keep going. Because once that question is asked, something shifts. Curiosity begins to look for structure. Feeling begins to reach for understanding. And slowly, almost gently, we move from wonder into science. To begin answering how many worlds might host life, we first have to understand the scale of where we are. We live inside a galaxy known as the Milky Way. From where we stand, it appears as a faint band of light across the sky. Soft, almost fragile. But that appearance is deceiving, because this galaxy is enormous. It contains roughly 400 billion stars, not millions, not even billions in the way we casually use the word. 400 billion individual suns, each burning in its own region of space, each with its own story written in gravity and time. For a long time, we didn't know what surrounded those stars. Our own solar system felt unique, special, perhaps even rare. Planets were something we knew only from our immediate cosmic neighborhood. But that assumption didn't survive contact with better instruments. As telescopes became more precise, something remarkable happened. We began to notice subtle changes in starlight, tiny dimming events, almost imperceptible shifts. At first, they seemed insignificant, but with patience, patterns emerged. Those patterns revealed something profound. Planets are everywhere. Around many of those 400 billion stars, there are worlds. Some large and gaseous, swirling with storms. Others small and rocky, with solid surfaces like Earth. Some orbit close to their stars. Others drift far out in the cold. Some systems are orderly, others are chaotic. But the important realization is this: planet formation is not rare. It is a natural outcome of how stars are born, and that changes everything. Because if planets are common, then the next question becomes unavoidable. How many of those planets could support life? We begin with a simple chain of reasoning. If there are 400 billion stars, and even half of them have planetary systems, that already gives us 200 billion potential systems. Now, within those systems, not every planet will be suitable. Many will be too hot, too cold, too unstable. But even if only a small fraction, say 1 in 5, hosts a planet with conditions that might allow life, we are no longer talking about isolated possibilities. We are talking about tens of billions of potentially habitable worlds. Let that settle for a moment. Tens of billions. It's a number so large it resists intuition. You cannot picture it. You cannot meaningfully compare it to everyday experience. And that is precisely why it matters, because it forces a shift. At the beginning, you were simply looking at the sky, feeling something you couldn't name. Now, you are standing inside a framework that suggests something extraordinary. The conditions for life may not be unique to Earth. They may be woven into the fabric of the galaxy itself. This is where emotion and logic meet. The feeling you had at the start, the quiet sense that the night sky holds more than emptiness, is no longer just poetic. It is supported, at least in part, by observation and inference. But this is not certainty. It's possibility. And possibility at this scale is powerful, because even if only a tiny fraction of those billions of worlds actually develop life, even if life is rare, fragile, and difficult to sustain, the sheer number of opportunities changes the equation. It suggests that somewhere, under a different sky, chemistry may have crossed the same threshold it did here, that molecules may have organized into something that persists, adapts, and perhaps even wonders. Not necessarily like us, not with our senses, our thoughts, or our understanding, but alive in its own way, and perhaps, just perhaps, capable of looking up at its own sky and asking a question that feels strangely familiar. How many worlds are out there, like mine? The journey from that first glance at the stars to this realization is subtle. There is no single moment where everything changes. Instead, it unfolds slowly, like the night itself, deepening, expanding, revealing more the longer you stay with it. We began with silence. We moved into scale. And now we stand at the edge of something larger than either. A universe that may not only contain life, but may be shaped in such a way that life is an expected outcome, given enough time and the right conditions. That doesn't answer the question completely, but it transforms it. Because now, instead of asking whether life could exist elsewhere, we begin to ask how often it does, and what that means for us. And perhaps most importantly, it reminds us that the simple act of looking up was never as simple as it seemed. That realization that the galaxy may be filled with billions of potentially habitable worlds did not appear all at once. It was not the result of a single discovery or a sudden breakthrough. It emerged slowly, almost reluctantly, from a series of careful observations that forced us to reconsider what we thought we knew. For most of human history, planets beyond our solar system were purely speculative. We could see the stars, chart their movements, even understand their life cycles to some degree, but the idea that they might host their own systems of worlds remained unproven. It was easy, in that long stretch of uncertainty, to assume that planets might be rare, that our solar system, with its orderly arrangement of worlds, was something unusual. But the universe, as it often does, had other plans. The shift began not with images, but with patience. Astronomers turned their attention to distant stars and began watching them not for what they revealed directly, but for what they hinted at indirectly. Because planets, especially small ones, are almost impossible to see across such vast distances. They do not emit their own light. They are overshadowed by the brilliance of the stars they orbit. So instead of trying to see the planets themselves, scientists looked for their effects. One of the most elegant methods is known as the transit method. It requires nothing more than time, precision, and a willingness to wait. A telescope is fixed on a distant star, and its brightness is measured continuously. For days, weeks, even months, nothing changes. And then, for a brief moment, the light dips, just slightly, almost imperceptibly. That tiny dimming is a shadow. A planet has passed between its star and our line of sight, blocking a fraction of the light. From that brief event, an extraordinary amount of information can be extracted. The size of the planet, its orbital period, even hints about its atmosphere, all inferred from a flicker that lasts only hours. There is something deeply human about this method. The idea that from such a small signal, a subtle decrease in light, we can reconstruct an entire world. It speaks to a kind of quiet intelligence, a way of listening carefully enough that even the faintest whisper becomes meaningful. Another method approaches the problem from a different angle. Instead of watching for shadows, it watches for motion. This is the radial velocity method, sometimes described as the wobble of a star. Planets do not simply orbit stars, they and their stars orbit a shared center of mass. As a result, the star itself moves ever so slightly, forward and backward, in a gentle rhythm. That motion affects the light we receive. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts toward red. These changes are incredibly small, but with precise instruments, they can be detected. From that subtle oscillation, astronomers can determine the presence of an unseen companion. They can estimate its mass, its orbit, and begin to map the structure of a system that cannot be directly observed. Between these two methods, watching for shadows and measuring motion, something remarkable has happened over the past few decades. We have gone from knowing 0 planets beyond our solar system to cataloguing thousands. Not a handful, not a rare exception. Thousands of confirmed exoplanets, with many more candidates waiting to be verified. Worlds of every kind. Gas giants skimming close to their stars, rocky planets locked in tight orbits, systems with multiple planets moving in intricate gravitational dances. The diversity alone is staggering. But more important than any single discovery is the pattern that emerges from them all. Planets are not unusual. They are a natural consequence of star formation. Wherever stars are born from clouds of gas and dust, leftover material tends to gather, collide, and gradually build into planets. It is not a rare accident. It is a process that repeats across the galaxy again and again. And with that realization, the question shifts once more. If planets are common and potentially habitable worlds are numerous, then what does it actually mean for a planet to be habitable? At first glance, the answer seems simple. We imagine a world like Earth, blue oceans, breathable air, moderate temperatures. But that image, familiar as it is, may also be limiting. Because life, as we are beginning to understand, is not defined by similarity to Earth. It is defined by its ability to emerge and persist under certain conditions. 3 conditions, in particular, appear to be essential. The first is energy. Life requires a source of energy to drive the processes that keep it going. On Earth, that energy comes primarily from the sun. It powers photosynthesis, shapes climates, and fuels the complex systems that sustain ecosystems. But energy does not have to come from starlight alone. It could arise from geothermal heat, chemical gradients, or other sources we are only beginning to explore. The second is chemistry. Life is built from matter, atoms arranged into molecules that can interact, replicate, and evolve. Carbon, water, and a range of other elanasa provide a flexible foundation for complexity. But even here, our understanding is incomplete. While Earth-based life relies heavily on carbon and liquid water, it is possible that alternative chemistries could support different forms of life under different conditions. The third is time. Even with energy and the right chemistry, life does not appear instantly. It requires long periods of stability, time for simple systems to become more complex, for patterns to emerge, for evolution to take hold. A planet may have all the right ingredients, but if its environment changes too quickly, life may never have the chance to establish itself. These 3 elements, energy, chemistry, and time, form a kind of framework, not a guarantee, but a set of conditions that make life possible. Within that framework, one concept has become especially important: the so-called Goldilocks zone. It is often described as the region around a star where conditions are just right. Not too hot, not too cold, but at a temperature where liquid water can exist on a planet's surface. Water, in its liquid form, plays a unique role. It acts as a solvent, a medium in which chemical reactions can occur efficiently. It transports nutrients, stabilizes temperatures, and supports the structures that living systems depend on. For these reasons, the search for life often begins with the search for water. But even this idea, useful as it is, can be misleading if taken too rigidly. A planet can lie within the Goldilocks zone and still be inhospitable. Its atmosphere might be too thin to retain heat, or too thick, trapping energy and creating extreme conditions. It might be bombarded by radiation, or locked in a way that leaves one side perpetually scorched and the other frozen in darkness. At the same time, life on Earth has shown us something unexpected. It is resilient. It exists in places once thought impossible, deep beneath the ocean floor, near hydrothermal vents where sunlight never reaches, in acidic lakes, in frozen environments, even within rocks miles below the surface. These extremophiles do not merely survive, they thrive under conditions that would be lethal to most known organisms. This suggests a possibility that expands our perspective. Perhaps life does not require a planet that looks like Earth. Perhaps it only requires an environment where energy flows, chemistry is active, and time allows complexity to emerge. If that is true, then the number of potentially habitable worlds may be far greater than our most cautious estimates. And once again, the question evolves. We are no longer asking only how many Earth-like planets exist. We are asking how many environments, across the vast range of conditions the universe provides, might allow life of any kind to take hold. It is a quieter, more open-ended question, and in many ways, a more profound one, because it does not seek to find reflections of ourselves, but to understand the full range of what life could be. As the idea of habitability expands, stretching beyond Earth-like conditions into a wider, more flexible framework, it becomes natural to ask a more grounded question. Where exactly are these possible worlds? Up to this point, everything has existed at the level of probability and inference. Vast numbers, statistical likelihoods, patterns drawn from distant light. But the human mind rarely settles with abstraction alone. It wants something more tangible, something it can almost picture. And slowly, over the past few decades, those abstractions have begun to take shape. One of the closest and most compelling examples lies just next door, in cosmic terms. A planet known as Proxima Centauri b orbits the nearest star to our Sun, Proxima Centauri. The distance between us and that star is about 4 light-years, a span so large it defies everyday comprehension, and yet, within the scale of the galaxy, it is almost intimate. A neighbor. Proxima b is a rocky planet, roughly similar in mass to Earth. It orbits very close to its star, completing a full revolution in just 11 days. At first, that might sound like a hostile arrangement. A tight orbit often means extreme heat. But Proxima Centauri is not like our Sun. It is a red dwarf, smaller, cooler, and dimmer. That changes the equation. Despite its proximity, Proxima b sits within what we call the habitable zone of its star, the region where temperatures might allow liquid water to exist, at least under the right atmospheric conditions. We do not yet know if it has an atmosphere. We do not know if it has oceans, clouds, or anything resembling a stable climate. But we know it is there, a solid world, orbiting a real star. Close enough, in cosmic terms, that its existence no longer feels hypothetical. It becomes something you can almost imagine standing on, looking up at a dim red sun, under a sky that may never fully brighten. And then there are systems even more extraordinary. Farther out, about 40 light-years away, lies a star system known as TRAPPIST-1. At first glance, the star itself is unremarkable. Small, faint, easy to overlook among the countless points of light. But what surrounds it has changed how we think about planetary systems. 7 planets, all roughly similar in size to Earth, all orbiting their star in tight, compact paths, like beads threaded on an invisible string. The entire system is so condensed that all 7 planets orbit closer to their star than Mercury does to our Sun. It is a different architecture, a different rhythm of motion. Among those 7 worlds, at least 3 lie within the habitable zone. 3 places where, under the right conditions, liquid water could exist. 3 chances, within a single system, for life to potentially take hold. Try to hold that image for a moment. A sky from the surface of one of those planets would not be empty. Neighboring worlds would appear large and close, sometimes hanging in the sky like luminous companions. Tides, gravitational interactions, subtle shifts in light, all part of a dynamic, interconnected system. It no longer feels like speculation. It feels like geography. These discoveries do something important. They transform the conversation. Instead of speaking in distant probabilities, we begin to speak in specific names, distances, and characteristics. The idea of habitable worlds is no longer an abstract category. It becomes a collection of places, each with its own conditions, its own possibilities. Each one a story waiting to be understood. And yet, for all this progress, something remains strangely unchanged. We have not found life, not a signal, not a microbe, not even a clear chemical signature that can only be explained by biological activity. Despite thousands of discovered planets and increasingly sophisticated tools, the universe, so far, remains silent on that question. This is where a quiet tension begins to build. Because on one hand, the numbers suggest abundance. Billions of stars, billions of planets, many of them potentially habitable. The statistical argument leans toward life being not just possible, but likely. And on the other hand, observation offers nothing definitive, no confirmation. This gap between expectation and evidence is one of the most intriguing aspects of modern astronomy. It does not resolve easily. It lingers, unresolved, inviting deeper reflection. But before we rush to conclusions, it helps to look back at the one example we know best: Earth. Here, life is not fragile in the way we once imagined. It is not confined to narrow, delicate conditions. Instead, it demonstrates a remarkable resilience, a capacity to adapt, persist, and even flourish in environments that seem, at first glance, entirely hostile. Deep beneath the ocean, where sunlight never reaches, entire ecosystems thrive around hydrothermal vents. These environments are fueled not by solar energy but by chemical reactions, heat and minerals rising from the Earth's interior. In frozen regions, organisms survive in ice for thousands of years, slowing their processes to match the harsh conditions. In acidic lakes, in radioactive zones, in places of crushing pressure and searing heat, life finds a way to continue. It does not demand perfection. It works with what is available. This realization complicates the picture, because if life can exist under such extreme conditions here, then the range of environments that might support life elsewhere becomes much broader. Worlds that once seemed uninhabitable may, under a different perspective, hold potential. Subsurface oceans beneath icy crusts, atmospheres rich in chemicals we consider toxic, planets locked in tidal rotations with narrow bands of survivable conditions between extremes. Each of these scenarios, once dismissed, becomes plausible, and with each expansion of possibility, the tension deepens. If life can emerge in so many ways, across such a wide range of conditions, then why have we not found it? There are many possible answers. Perhaps life is indeed rare, requiring a combination of factors so specific that it occurs only occasionally. Perhaps it exists, but at scales or in forms that are difficult to detect with current technology. Perhaps the signals are there, but we do not yet know how to recognize them. Or perhaps, though this is harder to accept, the silence is real. Not empty, but quiet in a way we do not yet understand. What matters, at this stage, is not choosing one answer over another, but recognizing the shape of the problem. we are caught between two powerful ideas. On one side, a universe rich with opportunity, vast, dynamic, filled with worlds that meet the basic conditions for life. On the other, a lack of direct evidence. And in that space between them, something important happens. We begin to think not just in terms of possibility, but probability. Not simply asking, could life exist, but how often does it emerge given the chances available? It becomes a question of patterns, of likelihoods, of thresholds we do not yet fully understand, and perhaps that is where the story becomes most compelling. Because we are no longer standing at the beginning, wondering if there are other worlds. We have found them. We have measured them, named them, begun to understand their nature. Now, we are standing at the next threshold, waiting, listening, refining our tools and our questions, looking out across a galaxy that feels more populated than ever before, and yet, in one essential way, still profoundly unknown. By this point, the question has changed shape so many times that it almost feels like a different question entirely. We began with a feeling, standing beneath a quiet sky, sensing that the darkness above us might not be empty. Then came the scale of the galaxy, the discovery of planets beyond our solar system, the expanding definition of what it means for a world to be habitable, and the unsettling tension of not yet finding life elsewhere. Now the mind does something inevitable. It starts to calculate, not with certainty, but with structure, not to reach a final answer, but to understand the range of possibilities in a way that can be measured, even if only approximately. We begin again with the number that anchors everything, roughly 400 billion stars in the Milky Way. It is not a poetic number. It is an estimate, refined over decades of observation, and while it may shift slightly with new data, its order of magnitude is stable enough to serve as a foundation. From there, we apply what we have learned. Observations suggest that planetary systems are common, so common in fact that it is reasonable to assume that at least half of all stars host planets. Some estimates suggest even more, but we remain conservative. Half of 400 billion. That gives us around 200 billion stars with planetary systems. Already, the number feels large, but this is only the first step. Within those systems, not every planet is a candidate for life. Many are gas giants, too massive to have solid surfaces. Others orbit too close to their stars, where temperatures rise beyond what most chemical structures can withstand. Still others drift too far away, locked in deep cold. So we narrow the field again. We look for rocky planets, worlds with solid surfaces, capable of holding atmospheres. And among those, we focus further on planets that reside within the habitable zone, where conditions might allow liquid water to exist. Current estimates suggest that perhaps 1 in 5 planetary systems could host such a world, 20%. Applied to our previous number, that leads us to something remarkable. Tens of billions. Not a vague suggestion, but a structured inference. Tens of billions of planets within a single galaxy that may possess conditions broadly compatible with life. It is, in many ways, the logical peak of everything we have built so far. Each step grounded in observation, each assumption restrained, cautious. And yet, even under these constraints, the conclusion is expansive. The universe, at least on the scale of our galaxy, does not appear to be short on opportunity. But numbers, no matter how large, are still abstractions. They describe possibility, not experience. And so, once again, the perspective shifts. Instead of asking how many worlds might exist, we begin to ask where they exist, what kind of structure contains them, what kind of environment shapes their formation, their evolution, and their fate. To answer that, we have to step even further back, far enough that individual stars disappear into patterns, far enough that planets, even entire systems, become invisible. What remains is the galaxy itself, not as a collection of points, but as a form, a structure. The Milky Way is not random. It is organized. though not in a rigid or mechanical sense. It has regions, layers, and gradients, each contributing to the conditions that make stars and planets possible. At its center lies something difficult to imagine: a supermassive black hole, Sagittarius, a star with a mass millions of times greater than our Sun. It does not dominate the galaxy in a visible way, but its gravitational influence anchors the entire system. Around it, stars move in dense, complex orbits, forming a crowded central bulge. This region is intense, radiation levels are high, stellar interactions are frequent. It is a place of energy and motion, but not necessarily stability. For life, as we understand it, such conditions may be challenging. Moving outward, the galaxy flattens into a vast, rotating disk. This is where most of the stars, including our Sun, reside. The disk is not uniform. It is marked by spiral arms, sweeping structures rich in gas and dust. These arms are regions of ongoing creation, where new stars are born from collapsing clouds of material. Within these regions, planetary systems begin to form. Dust grains collide and stick together. Over time, they grow into larger bodies, planetesimals, then protoplanets, and eventually fully formed worlds. It is a slow, complex process, influenced by gravity, collisions, and the distribution of material within the disk. The disk is dynamic. Stars orbit the galactic center, but not all at the same speed. Over millions of years, their positions shift, their environments change. A star that forms in one region may, over time, drift into another. The galaxy is not static, it evolves. Beyond the disk lies the halo, a vast, diffuse region extending far above and below the plane of the galaxy. It contains older stars, globular clusters, and dark matter, an invisible component that contributes significantly to the galaxy's mass. The halo is quieter, less dense, but also less rich in the heavy elements needed to form complex planets. Together, these components, core, disk, and halo, create a layered system. Not all parts are equally suited to the formation of life. In the inner regions, conditions may be too extreme. In the outer halo, too sparse. Between these extremes lies a kind of balance, a region where stars are common but not overcrowded, where heavy elements are available but not overwhelmed by radiation or instability. Our solar system resides in this middle ground, not at the center, not at the edge, but somewhere in between. A position that, over billions of years, has allowed conditions to remain relatively stable. It is not the only such region, and that realization invites a different kind of comparison. Imagine the galaxy not as a fixed structure, but as an ocean. The central bulge becomes a turbulent current, dense, energetic, constantly in motion. The spiral arms are like shifting waves, regions where material gathers and disperses. The outer halo is a quiet expanse, vast but thin, where little happens. And within this ocean, stars are like islands, some isolated, some part of clusters, each surrounded by its own system of worlds, its own local conditions. Some islands lie in stormy waters, others in calmer seas, and scattered among them, perhaps, are the rare environments where life can emerge and persist. From this vantage point, the earlier numbers take on a new meaning. Tens of billions of potentially habitable planets are not just a statistic. They are locations within this ocean, points distributed across a structure that is both ordered and dynamic. They are not evenly spread. They are shaped by the galaxy's architecture, by where stars form, how they move, and what materials are available to them. And so the question deepens once more. It is no longer only about how many such worlds exist, but how they are distributed, how they evolve, and how the larger structure of the galaxy influences their potential for life. We have moved from the ground to the sky to the stars, from the stars to planets, and now from planets to the galaxy itself. Each step widening the perspective, each step revealing that what once seemed like a simple question is, in fact, part of a much larger system, one that operates across scales so vast that even our most careful estimates only begin to capture its complexity. And yet, despite that scale, despite the abstraction, the origin of all this remains the same. A single moment, a quiet night, a person looking up and wondering if the darkness is truly empty or quietly full of worlds waiting to be understood. And after all of this, after the numbers, the distant systems, the slow expansion of what we consider possible, something subtle begins to shift again. The direction of the question turns inward, because when you look at the galaxy as a whole, its structure, its scale, its countless stars and potential worlds, it becomes difficult to hold on to the idea that we stand apart from it. The separation begins to dissolve. Our planet, Earth, feels vast when measured against mountains, oceans, and the span of human history. But against the backdrop of the galaxy, it shrinks to something almost invisible. A small, rocky world orbiting an ordinary star located in a quiet region of a spiral arm, one among hundreds of billions. A speck. And yet, that is only one way to see it, because the same processes that shaped the galaxy also shaped us. Long before Earth existed, before the sun ignited, the universe was already at work, building the Alanasa that would one day make life possible. In the cores of ancient stars, lighter elements fused into heavier ones: carbon, oxygen, nitrogen, iron. When those stars reached the ends of their lives, many of them exploded, scattering their contents back into space. Those remnants did not disappear. They became part of new clouds of gas and dust. From those clouds, new stars formed, new planets coalesced, and on at least one of those planets, the chemistry became complex enough to give rise to life. Everything that composes the human body, every atom, has passed through this cycle. You are not merely in the universe, you are made of it. This is not metaphor, it is a physical continuity. The calcium in your bones, the iron in your blood, the carbon in every cell, all of it forged in stellar environments long before the Earth existed. And when you consider that, the relationship between observer and observed begins to change. The universe is not something entirely separate, waiting to be studied from a distance. In a very real sense, it has produced a system, us, that is capable of turning back and asking questions about its own origin and structure. A kind of loop. Matter organizing into life, life organizing into awareness, awareness directing itself outward, attempting to understand the conditions that made it possible. From this perspective, the question of whether we are alone takes on an additional dimension. It is no longer only about finding other forms of life, but about understanding how often the universe produces systems that can reflect on themselves in this way. How often does the universe become aware of its own existence? That question does not yet have an answer, but it leads naturally into the next phase of the journey, the methods we use to approach it. Because everything we have discussed so far, the detection of distant planets, the estimation of habitable worlds, the mapping of the galaxy, has been made possible by tools, not tools of physical travel, but tools of perception. We cannot cross the distances between stars. Not yet. Perhaps not for a very long time. But we have found another way to reach outward. We observe. Telescopes, in their simplest form, are extensions of the eye. They gather more light, resolve finer detail, allow us to see objects that would otherwise remain invisible. But modern instruments go far beyond simple magnification. They analyze light, breaking it into spectra, measuring its intensity, tracking its changes over time. From light, we extract information: the composition of a star's atmosphere, the presence of elements on a distant planet, the movement of objects we cannot see directly, even hints of atmospheric chemistry, gases that might suggest biological activity. It is a remarkable process. A photon leaves a distant star, travels across space for years, sometimes for thousands or millions of years, and eventually reaches a detector on Earth. From that single particle of light, we begin to reconstruct an entire environment, a world inferred from a signal. Spacecraft extend this process further. They carry instruments beyond Earth's atmosphere, removing the distortions caused by air and weather. Some travel to other planets within our solar system, studying their surfaces, their atmospheres, their histories. Others remain in orbit, continuously observing distant regions of space with precision that would be impossible from the ground. Together, these tools form a network of observation. They do not eliminate uncertainty, but they reduce it. They allow us to move from speculation to measurement, from imagination to evidence. And in doing so, they make something else possible. They allow us to ask better questions. Because science, at its core, is not simply a collection of answers. It is a method for refining questions, making them more precise, more testable, more aligned with the structure of reality. We began with a question that felt almost philosophical. Are we alone? Now that question has branches. How many habitable planets exist? What conditions allow life to emerge? How can we detect biological signatures from a distance? What patterns should we expect if life is common or rare? Each of these questions leads to experiments, observations, and new data. And each answer, partial as it may be, reshapes the landscape of what we know. But there is a limit, at least for now. Despite all our instruments, all our measurements, all our models, the central question remains unresolved. We have not yet found definitive evidence of life beyond Earth. And that brings us to the final shift. Not in method, not in scale, but in meaning. Because it is tempting to think that the value of this entire exploration lies in the answer. That once we know whether life exists elsewhere, the question will be complete. But that may not be entirely true. There is something else happening along the way. The act of asking the question, of looking outward, of building tools, of refining our understanding, changes us. It alters how we see our place in the universe, how we understand our origins, how we relate to the world around us. It replaces certainty with curiosity. It transforms isolation into connection, not because we have found others, but because we begin to see ourselves as part of a larger process. In that sense, the journey is not only about discovery, it is about perspective. The universe may be vast beyond comprehension, stretching across distances we cannot traverse. It may feel distant, unreachable, almost abstract. And yet, at the same time, it is intimately present. In the atoms that make up our bodies, in the light that reaches our eyes, in the questions that arise when we look up at the night sky and wonder, far away and very close, both at once. And perhaps that is where everything returns to its beginning, not with a final answer, but with a simple act. A person standing under a quiet sky, asking a question that seems small in the moment, but carries within it the possibility of understanding something immense. Because every discovery we have made, every theory we have built, every instrument we have designed, began the same way, with a question, and the willingness to follow it wherever it leads.